Have you ever looked at a super complex equation and just wondered, how on earth does a computer solve this? Especially when there might be a bunch of different correct answers, but it just spits out one. And you didn't even tell it how to solve it, step by step. Well, I promise you, it's not magic. It's a really cool process, and we're going to break it all down. Believe it or not, it all begins with just one thing, a guess. From that single guess, the software starts this incredible journey, taking one step after another, getting closer and closer to the real answer each time. In this explainer, we're going to follow that journey from the very first guess all the way to the final solution, and you're going to see why you are actually the most important piece of this whole puzzle. Okay, so to really get this, we first have to understand the tool itself. We're talking about software like the Engineering Equation Solver, or EES for short. And here is the absolute key. This is not a programming language. It doesn't think like one at all. It approaches problems from a completely different angle. Think about it like this. A normal programming language is like a cook following a recipe. You give it the exact ingredients, a clear list of steps, and boom, you get a result. But an equation solver? It's more like a detective. You hand it a mystery, an equation with all these unknown variables, and its job is to find the values that make the whole story make sense. It's not following orders. It's hunting for clues. So how does our software detective start cracking the case? Well, here's the really clever part. It doesn't try to solve the whole messy equation all at once. Nope. Instead, it totally reframes the problem and gives itself a much, much simpler mission. It does this with a concept called a residual. And it sounds technical, but it's super simple. All the software does is move everything from the right side of the equal sign over to the left side. Now, if the two sides were perfectly balanced, what would the equation equal? 0, right? Well, that leftover amount, that's the residual. And when you can make that residual 0, you've solved the equation. And just like that, that's the new mission. The software's entire complex purpose gets boiled down to this one simple objective. Find the value that makes that residual hit 0. That's the target. That's the bullseye. But here's where things get tricky. For these really complex equations, there often isn't just one right answer. Think of a curvy road crossing a straight river. It might cross over in a few different places, right? Same idea here. On this chart, each one of these blue dots is a spot where the residual hits 0. They're all valid solutions. The challenge for the software is that it's only going to find one of them, and which one it finds depends completely on where it starts its search. So, let's actually follow that journey. How does it get from a random guess to a perfect answer? The solver uses a really powerful technique called Newton's method to find its way. Now, that might sound complicated, but the idea behind it is actually surprisingly intuitive. It's all about taking smart steps. So here's the game plan. First, it makes an initial guess. That's our starting point. Then it calculates the residual, basically asking, okay, how far away am I from 0? Step 3, and this is the magic sauce. It figures out the slope of the curve right at that guess. That slope tells it which way is downhill towards 0. Step 4, it uses that slope to make a new, much smarter guess. And then it just does it all over again. Repeat, repeat, repeat. All right, let's watch this thing in action. We're the user, so we have to provide the starting point. Let's just say our first guess for x is 2. The solver takes that number, plugs it in, and boom, it's on the map. The journey has officially begun. And right away, we get our first piece of feedback. See that red dot? That's the residual for our guess. And yeah, it's not on the 0 line. We're not there yet, not even close, but that's okay. We've established our position. We know how far off we are. Now for the really brilliant part. The solver looks at our exact position on the curve and calculates the slope right there. You can think of this slope as a compass needle. It instantly points the most efficient way down towards that 0 line. This is the key to making an intelligent next move instead of just guessing randomly. So, following the direction from its compass, the solver projects a straight line down until it intersects the 0 axis. And bam! That intersection point becomes its new, much more informed guess for x. I mean, look at that. In just one step, look how much closer we are to an actual solution. And from here, the whole loop just becomes this powerful engine of refinement. From this new, better guess, it calculates a new, smaller residual. It finds the new slope at that point. It projects down to find an even better guess. Each time it repeats this cycle, it just homes in on the target with incredible precision. This process is super efficient, but it can't go on forever, right? So how does the solver actually know when to stop? Well, there are a few built-in stop signs. The journey might end after a set number of attempts, or if it's just taking too long. But more often, it stops when the residual gets so incredibly small it's practically zero, or when the difference between one guess and the next becomes microscopic. That's when the solver knows it has finally arrived at its destination. Now, this method is powerful, but it is not foolproof. The success of this entire journey hinges almost completely on where it begins. A bad starting point can send the solver on a total wild goose chase. So, the big question is, does this always work? The short answer is no, absolutely not. And understanding why it can fail is the key to using these tools effectively. A bad initial guess can be a complete disaster. It can cause the solver to diverge, meaning it gets further away from the answer with each step. It might land on a point where the slope is zero, causing a division by zero error that crashes the program. Or it might even find a solution that's mathematically correct but makes no sense in the real world, like a negative length or a negative time. And this brings us right back to your role. Remember those multiple solutions? If you start your guess on the left side of this hump on the graph, the solver will inevitably find the solution on the left. But if you start on the right, it will find that completely different solution on the right. Both are mathematically correct, but only one might be the answer you're actually looking for. All of this leads to a final, crucial point. The software is doing all this complex math at lightning speed, but it's fundamentally blind. It doesn't know what it's looking for. It needs a guide. And that guide is you. The source material really puts it perfectly. It says, the choice of the guess value that you use to start the iteration process is very important. That's almost an understatement. It doesn't just influence the journey, it basically determines the destination before you even start. So, your job isn't to solve the equation yourself. Your job is to be the expert. You use your knowledge of the problem to give the solver a reasonable starting point, to tell it which neighborhood it should even be searching in. You don't do the heavy lifting, but you point this powerful but blind solver in the right direction. In the end, this solver is an incredibly powerful tool. It's an engine that can navigate the most complex problems. But it can't read a map. You're the one holding that map. You're the one who tells it where to begin. So the real question isn't how powerful the solver is, it's how well you can guide it.